All right, let's dive into one of the absolute cornerstones of software engineering, system design. We're going to go on a pretty cool journey today, taking an app from just a little project sitting on one computer all the way up to a massive, worldwide distributed system. So let's get started.
So picture this. You launch your app, and boom, overnight, it just blows up. Millions of people are downloading it. I mean, this is the dream, right? But that dream can turn into a total nightmare fast if your system isn't built for it. And this one question, right here, is exactly why we need to talk about system design. Before you can build, a skyscraper that's not going to fall over, you need a plan, a blueprint. In the world of software, that blueprint is our system design. And just like building a house, there are different levels of detail we need to think about.
So what is it, really? At its heart, system design is just the process of figuring out all the pieces of the puzzle. The architecture, how the different parts talk to each other, where the data goes, all to make sure the system actually does what it's supposed to do. It's all about making smart choices up front so your app doesn't fall apart later.
And we can break this down into two big categories. You've got high-level design, or HLD. Think of this like the main blueprint for a house. It shows you where the kitchen is, where the bedrooms are, and how you get from one to the other. It's the big picture stuff, scalability, availability. Then you have low-level design, or LLD. This is more like the detailed plan for just the kitchen, what kind of pipes to use, how the wiring works, the specific algorithms. For our purposes today, we're going to be focusing on that big picture, the high-level design.
Okay, so let's get back to our viral app. It's running on one single server, and you can practically see the smoke coming out of it. This is our first huge growing pain, and it's time to fix it.
The problem itself is pretty simple. Way too many people are trying to get through the same door at the same time. The server's CPU is pegged at 100%, it's out of memory, and your users, well, they're seeing a lot of error pages. It's what we call a single point of failure, and yep, it has failed.
This is what we started with. Super simple, clean, and honestly, it was perfect when we launched. But it was built for day one, not day 100. Every single user is hitting that same tired, overworked machine.
So what's the solution? It's actually really elegant. We introduce a load balancer. The best way to think about this is like a traffic cop for your application. Instead of letting all the cars jam up one single street, the cop starts directing them down a few different, less crowded streets. This is our very first step into the world of distributed systems. And here's what it looks like now. The user's request first hits the load balancer. Then, that load balancer makes a smart decision about which of our servers, and now we have several, is best equipped to handle it. And you know what's really cool? If one of those servers goes down, it's no big deal. The traffic cop just stops sending cars that way. Instantly, our app is way more available. But for all you senior engineers out there, here's where it gets even more interesting. It's not just about having a load balancer, it's about how it makes its decisions. Is it using a simple round-robin method, where it just gives each server a request one by one? Or is it using something smarter, like least connections, where it sends the new request to the server that's doing the least amount of work? At scale, that choice has massive performance implications.
Okay, great. We've solved the web server problem. But all we've really done is reveal the next bottleneck in the chain. Now all our happy, healthy web servers are all hitting the same single database. And guess what? Now it's the thing that's slowing to a crawl. So let's fix that.
We've got two main weapons in our arsenal for this fight: replication and sharding. Let's talk about replication first. The idea here is pretty straightforward. We make copies, or replicas, of our database. We can set one as the master database. All new data gets written there. And then all the slave replicas can handle the job of serving up data for people to read, which usually happens way more often.
But what happens when your data gets so huge that it can't even fit on one machine anymore? Well, that's where sharding comes in. And here's a great analogy. You wouldn't try to use one giant phone book for the entire country, right? It'd be impossibly huge. Instead, you have smaller phone books for each state. That's all sharding is. We're breaking up our data into smaller, more manageable, independent chunks.
And just like with everything else, how you do it matters. You could do range-based sharding, but you might create hotspots where one server gets all the traffic. Hash-based is a bit better for distribution, but adding new servers can be a total pain. That's why today, the gold standard is something called consistent hashing. It's a really clever algorithm that lets you add or remove servers without having to move all your data around. It's a real game changer at scale. So far, everything we've talked about has been a practical solution to a specific problem. But what's fascinating is that these solutions are all governed by some fundamental laws. They're almost like the laws of physics for distributed systems. And it's time to talk about the most famous one of all, the CAP theorem.
So when you're building a distributed system, there are three things you really want. But here's the catch. You only get to pick two.
So, what are these three amazing things? They are consistency, availability, and partition tolerance. Consistency means that anytime anyone looks at the data, they see the most recent, up-to-date version. Availability means your system is always online and ready to respond. And partition tolerance means your system doesn't just crash and burn if the network connection between two of your servers breaks.
But here's the real kicker. It's not actually a choice between three things. Because in any real system, network failures, partitions, are just a fact of life. They are going to happen. You can't wish them away, so you don't really get a choice. You must design for partition tolerance. And that means the real, agonizing choice is always between consistency and availability.
The best way to get your head around this is with a Google Doc. Okay, imagine Alice and Bob are both editing a document, and suddenly Bob's internet connection drops. If the system chooses availability, it lets both of them keep typing. The service is available to them. But now you've got two different versions of the document that have to be merged later. That's an AP system. But what if it chooses consistency? In that case, the system locks the document for Bob until his connection is back. The data stays perfectly consistent, but for Bob, the service is totally unavailable. That's a CP system.
But wait, the trade-offs don't stop there. The CAP theorem is all about what happens during a network failure. But what about the other 99.9% of the time, when everything is working just fine? Well, it turns out there's another trade-off happening then too, and that's where the PACELC theorem comes into play.
PACELC is a really cool extension of CAP. It basically says, if there's a partition, you have to choose between availability and consistency. That's the PAC part. Else, when the network is fine, you face a totally different choice. You have to choose between latency and consistency, basically a choice between speed and correctness.
Let's dig into that else choice because we deal with it every day. When you like a photo on Instagram, you want that little heart to fill in instantly, right? You're choosing low latency, even if it takes a couple of seconds for your friend across the world to see that updated like count. But now think about making a bank deposit. Do you want that to be fast or do you want it to be correct? You absolutely want the system to take its time, verify everything, and guarantee the money is there before your balance gets updated. You're choosing high consistency.
And this framework is so powerful because we can actually classify entire database systems by the choices they make. Take a look at that first row. A P/EC system chooses consistency during a partition and consistency during normal operation. These are your classic relational databases. They value correctness above all else. Now look at the second row, the PA/EL systems. They choose availability during a partition and low latency when things are running smoothly. This is the world of NoSQL databases like DynamoDB or Cassandra, systems built for insane speed and uptime.
So as you start to think about designing your next system, it really all boils down to this fundamental question. Do you need the lightning-fast response of an Instagram like, or do you need the absolute rock-solid certainty of a bank transaction? Are you building for speed, or are you building for certainty? Because, as we've just seen, you can't always have both, and the answer you choose will define absolutely everything about the system you build.